Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we are starting a deep dive into one of the most foundational topics in electrostatic potential and capacitance, equipotential surfaces. Our mission today is to give you a simple conceptual understanding that is absolutely exam safe and, well, unforgettable. So we have been discussing electrical potential, which is, basically the electrical equivalent of gravitational height. Now let's start with a simple thought experiment. Imagine you are moving a box on a floor. If that floor is perfectly level, a perfectly flat equipotential surface for gravity, how much work do you do against a gravitational force?
None, right. Assuming there's no friction, of course. We only spend energy and do work if we lift the box up or if the floor slopes, meaning we change our elevation.
Precisely. That level floor means the gravitational potential is the same everywhere. Now, here is the surprising connection to electricity. Something our source materials really highlight. The principle behind a Faraday cage. Why is sitting inside a metal car during a thunderstorm actually the safest place to be, even though that metal is a superb conductor?
That feels counterintuitive. Because we are taught metals should attract the lightning strike, it must have something to do with how the charge behaves on the conductor's surface.
It does. The critical point is that when lightning strikes or a massive charge builds up nearby, the metal casing instantly allows charges to redistribute. They move until the entire structure, including the air inside, becomes a giant single equipotential volume.
So if the entire volume has the same potential, say, 1,000 volts, then the potential difference across any 2 points, including my body inside, is zero.
Exactly. And if the potential difference is zero,
No work can be done.
no work can be done on you by the field, meaning no force acts on the charge in your body. We need to understand the concept of equipotential surfaces to prove why you are completely safe inside that electrical flat path. Okay, let's unpack this core idea now, the term equipotential surface. It breaks down simply. Equi means equal, and potential, well, that means electrical potential V. So the core idea is straightforward. It is any surface, real or imaginary, where the electric potential V has the exact same value at every single point on it. To visualize this, let us return to that analogy we love so much, the geographical contour map. You've definitely seen these maps where lines connect points of equal elevation. Every point on the 100-meter contour line is at 100 meters above sea level.
So an equipotential surface is like a three-dimensional contour shell. It maps all the points of equal voltage in space.
You got it. And the reason this concept exists is not just for definition. It is to give us the single most visual and powerful way to map the invisible electric field. Without equipotential lines, the field lines are just abstract arrows. With them, we instantly map the field's direction and, crucially, its strength. Picture the mental image around a positive point charge. Imagine invisible, nested bubbles surrounding it, like the layers of a spherical onion. The surface of each bubble is one equipotential surface. If you try to move a test charge, a small marble, along the surface of one bubble, you do zero work.
But the marble must want to move away from the central positive charge, right? Towards a bubble with a lower potential value.
That is the crucial insight. It wants to roll perpendicularly away. This rolling through direction instantly shows you the path of the electric field line. The field line always wants to push the charge from high potential to low potential.
Just as gravity pulls water from a high altitude to a low altitude.
Perfect. So the key takeaway is that the potential V must be constant.
And since potential energy U equal QV, if V is constant, the potential energy U for any charge Q placed on that surface must also be constant.
Precisely. This constancy of energy is the physical cornerstone that leads to the most important property of equipotential surfaces. Now let us look at the formal language you need to use in your board exams. An assert defines this very clearly. Can you please read the formal definition from the text?
An equipotential surface is a surface with a constant value of potential at all points on the surface.
Excellent. Now we connect this definition to the electric field itself, which is a three-step logical proof. This is essential for derivation questions. Step 1. By the definition you just read, the potential difference, delta V, between any 2 points A and B on this surface must be 0. Why? Because VA equals VB. Step 2. We know the work done, W, by the field in moving a test charge Q naught from A to B is defined as WAB naught times delta V, since delta V is 0.
The work done, W, must be 0. No change in height, no work done. That part is clear.
Step 3 is where the vector physics comes in, and it is the most critical link. We also have an alternative definition of work done in terms of the electric field vector E and the displacement vector dl. It is W is essentially E dot dl. L.
A dot product.
Yes, a dot product, and that's a great point to pause on.
I was going to ask, why the dot product here, not the cross product? I mean, isn't the cross product usually for things that are perpendicular?
That is an excellent question and a very common source of confusion.
Right.
We use the dot product because the definition of work done, W, only depends on the component of the force that is parallel to the displacement. The dot product, E dot dl, gives us exactly that, E dl cos theta, where theta is the angle between the field and the direction of motion. Now, we know from step 2 that W must be 0, so the equation becomes E dot dl equals 0. Since neither the electric field E nor the displacement dl is necessarily 0, the only way for the dot product to be 0 is if
Cos theta is 0.
Yes.
And cos theta is 0 when the angle theta is 90 degrees.
Exactly. So the most important property is proven. The electric field E must be normal, perpendicular, or at 90 degrees, to the equipotential surface at every point. If there were even a tiny component of the field tangential to the surface, that component would do work, moving the charge, and the surface would instantly stop being equipotential. Hope everything is clear so far. This concept explainer is from ProfSam.com. Now let us apply this perpendicularity rule to visualize the electrical landscape. This involves one of the most important conceptual insights: mapping field strength using surface density. Let's go back to our contour map analogy. Where contour lines are drawn very close together on a mountain, what does that indicate?
It means the mountain is very steep there. A steep slope means a strong gravitational force pushing you down.
Exactly. The same principle applies to equipotential surfaces in electricity. If the equipotential surfaces are closely spaced, it means the potential is changing very rapidly with distance, a steep electrical gradient. This indicates a very strong electric field, E. Conversely, where the surfaces are far apart, the field is weak. This link is a goldmine for multiple choice questions. Let's quickly look at 2 standard drawing examples for equipotential surfaces. First, for a single point charge Q. We know potential V is given by V equals 1 over 4 pi epsilon naught, Q over R. Since V depends only on the distance R, the equipotential surfaces are
Concentric spheres, centered at the charge.
perfect. So for a positive point charge, the field lines are radiating outwards, and the spherical surfaces are always perpendicular to those lines.
And following the density rule, since the field gets weaker as you move away, the spheres should get farther apart.
You're one step ahead, correct. The field strength of a point charge drops off as 1 by r squared. It gets weaker rapidly. So the equipotential spheres must get progressively farther apart as the radius r increases. This visually maps the field weakening. Now contrast this with the second example. A uniform electric field E, like the field you find between 2 parallel capacitor plates. Here, the field lines are parallel and equally spaced. So since the field is constant, the potential gradient must also be constant. Therefore, the equipotential surfaces are simply planes.
Parallel to each other and perpendicular to the field lines.
Exactly. And crucially, they must be equally spaced throughout the region. Okay, let's quickly confirm our zero work principle with a simple numerical example. Suppose you have a charge of, say, plus 3 microcoulombs. If you move it from point X to point Y, both of which lie on the 70-volt equipotential surface, how much work is done by the electric field?
Okay, so work W is Q times delta V. Since Vx equals Vy equals 70 volts, delta V is 0. So the work done W is 0 joules. The field does no work.
Fantastic. No matter how much charge we move or how long the distance is, that zero work proof and the resulting constant potential bring us back to our big application. Conductors. What physical state is a conductor always in when static charges are present?
A conductor is an equipotential volume.
Precisely. This link is vital for the next chapter. If we revisit our Faraday cage, we realize why the principle holds. Static charges within a conductor instantly redistribute until the electric field E inside is 0, and an E equals 0 condition forces the entire volume inside and on the surface to be at a single constant potential. Now, for the silent killers, these are 2 common misconceptions that trip students up and cost easy marks in the exam hall. Killer number 1. Students often assume equipotential surfaces behave like simple overlapping geometric shapes and can cross each other.
That sounds reasonable, though, like drawing 2 circles that intersect. Why is it physically impossible in physics?
It violates the fundamental definition of potential. If 2 equipotential surfaces, say surface 1 at V1 equals 50V and surface 2 at V2 equals 100V, were to cross, the single point of intersection would simultaneously have 2 different values of potential 50 volts and 100 volts. You cannot be at 2 different electrical heights at the same physical point in space. Potential is a scalar, single-valued function. Therefore, equipotential surfaces can never cross. Killer number 2, and this is a major one, linking back to conductors. Many students confuse zero field with zero potential. They think that because the electric field E inside a charged conductor is zero, the electric potential V must also be zero inside.
I could see why students think that.
Right.
If the field is zero, everything should be zero, right?
That is the flaw. They forget the mathematical relationship. E is the negative gradient of V. Think of E as the slope of the hill and V as the height of the hill. If the electric field, the slope, is zero, it doesn't mean the height, V, is zero.
That just means the height is flat.
It only means the height is flat, or constant. For a charged conductor, the field is zero inside, but the potential is constant and non-zero, equal to the potential on its surface.
Ah, I get it now. So the conductor is like a massive flat tabletop. The slope is zero, but the tabletop itself has a constant specific height above the ground. It's constant potential, not zero potential.
Perfect analogy. Always remember, E is zero means V is constant. This will save you marks. To anchor these critical concepts for life, let's look up 2 simple memory tools. For the relationship between the field and the surface, remember this catchy phrase, especially for your diagrams: field and surface always cross at 90. And to visualize this physically, try a gesture. Hold your hand flat, palm facing up. This represents the equipotential surface. Now, take a pen and stab it straight down, perpendicular to your palm. That is the electric field line.
And if the pen slanted, that would represent a tangential component of the field, and the charge would roll off, destroying the equipotential state.
Precisely. If you maintain that perpendicular relationship in your diagrams, you maintain the physics. Time now for a quick exam-ready recap with 3 factual bullets that summarize everything you need to know about equipotential surfaces. First, the definition. The electric potential V is constant everywhere on the surface. Second, the consequence for work. No work is done by the electric field in moving any charge along this surface. And third, the fundamental property for diagrams. The electric field E is always perpendicular or normal to the equipotential surface at every point. Remember, understanding this concept is vital not just for the final paper, but for comprehending how electric charges distribute themselves in the real world. From the microscopic scale to large safety devices like the Faraday cage. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. We will continue our deep dive into the detailed properties of conductors, starting with electrostatic shielding next time. Until then, keep those potential surfaces perpendicular.